Hello, hello, Shagath Unknown here. Let's do that one more time. Hello, hello, Shagath Unknown here. Welcome back to another Rust coding stream here on the 18th of January, 2023, local time 1702. I doubled up that intro there because I might have started speaking a little bit too quickly. As a little reminder, I don't know if I mentioned it on these coding streams, but if you're watching this on YouTube, I did something different where my recording now pauses when I'm on the BRB or the starting screen, and I may have started talking before it started recording. So there we go, a little scuffed intro. But yeah, what are we up to? Last time we changed how the spawning works. We kind of moved out of the map generation stuff and we started looking into more game design. So it's basically, here's a design document, and then once we have that in place, let's go ahead and remove some of the hard-coded stuff from the game, like our spawning, and build out like JSON spawn tables and stuff. That way we can change that without having to recompile. Although because the tutorial was targeting WebAssembly as well, we do still have to recompile technically, although it's kind of also possible to still read in the files. Basically, what happens is it will include, it'll pull those files in and actually include them in the binary. That way on WebAssembly, you have the stuff baked into your file, baked into the executable, so you don't have to try to read stuff off a system, which gets very messy. So we're still having to kind of do that, but if I stripped out the WebAssembly stuff, we could actually completely dynamically read that in without recompiling. So basically, it allows us to define in some nice text JSON rather than in our actual code what it is we want to spawn and how we want to spawn it and so on. So there's not really much to show here. I mean, we have a Cabal, which was something new. I just fought him right there. There's not really much to show here because it's really the same basic functionality, with simply a couple more items added just so we could test the new functionality. So rather than focusing any more on this, let's go ahead and start talking about making a town. So we have the starting town, as we're going to refer to it. The idea with our game, well, it's actually listed here, so we'll just read it. What is the town for? Back in the design document, we decided the game starts in town. In town, there are only minimal enemies, pickpockets, thugs. You start in the to-be-named pub, tavern, armed with only a meager purse, minimal starting equipment, a stein of beer, a dried sausage, a backpack, and a hangover. Town lets you visit various vendors. From a development point of view, this tells us a few things. The town has a story aspect, in that you start there and it grounds the story, giving a starting point. A destiny, in this case a drunken promise to save the world. So the town implies a certain cozy starting point, implies some communication to help you understand why you're embarking on the life of an adventurer, and so on. The town has vendors. That won't make sense at this point because we don't have a value/currency system, but we know that we need somewhere to put them. The town is a tavern/inn/pub. It's a starting location, but it's obviously important enough that it needs to do something. Elsewhere in the design document, we mention that you can town portal back to the settlement. This again implies a certain coziness/safety, and also implies that doing so is useful, so the services offered by the town need to retain their utility throughout the game. Finally, the town is the winning condition. Once you've grabbed the amulet of Yala, getting back to town lets you save the world. That implies that the town should have some sort of holy structure to which you have to return the amulet. The town is the first thing that new players will encounter, so it has to look alive and somewhat slick, or players will just close the window and try something else. It may also serve as a location for some tutorials. This sort of discussion is essential to game design. You don't want to implement something just because you can. In most cases, big open world games relax that a bit. The town has a purpose, and that purpose guides its design. I do like the mention, by the way, of the this implies the town should have some sort of holy structure to which you have to return the amulet. No, I think it'd be funny to just kind of, you return it to the most mundane place and just like nothing happens. It's like, oh, cool, thanks for the amulet. It's like, oops, that'd be like a humorous thing. But I think it wouldn't also be amusing if you just return it just like some random person, and they're like, oh cool, yeah, this is gonna save the world, and like maybe they do something, but it's so just like underwhelming. Like there's no big like special graphic or anything. It's just like, oh yeah, I'll take care of this. Like I've got the amulet, it's all done now. Thanks, appreciate it, bye. Anyway, so what do we have to include in the town? That discussion lets us determine that the town must include one or more merchants. We're not implementing the sale of goods yet, but they need a place to operate. We need some friendly/neutral NPCs for color, a temple, a tavern, a place that town portals arrive, and a way out to begin your adventure. We can also think a little bit about what makes a town. There's generally a communication route, land or sea, otherwise the town won't prosper. Frequently there's a market. Surrounding villages use towns for commerce. There's almost certainly either a river or a deep natural water source. Towns typically have authority figures, visible at least as guards or watch. Towns also generally have a shady side. So how do we want to generate it? We could go for a prefabricated town. This has the upside that the town can be tweaked until it's just right and plays smoothly. Oh, I was going to mention it. It's actually down here, so we'll keep reading. It has the downside that getting out of the town becomes a purely mechanical step after the first couple of playthroughs. Look at Yopa in Caves of Cud. It became little more than a grab the chest content, talk to these guys, and off you go speed bump start to an amazing game. So we want a procedurally generated town, but we want to keep it functional and make it pretty. Not much to ask. Making some new tile types. So from the above, it sounds like we're going to need some new tiles. The ones that spring to mind for a town are roads, grass, water, both deep and shallow, bridge, wooden floors, and building walls. One thing we can count on, we're going to add lots of new tile types as we progress, so we better take the time to make it a seamless experience up front. My personal aside, that's called refactoring, right? In this case, we're like pre-factoring. We're refactoring ahead of time because we want to make sure it's extensible for the future now. So I was going to mention something, and we're seeing a sneak peek at the bottom, but I'll still mention it anyway because I'm getting ideas on how this might be done. Map.rs could get quite complicated if we're not careful, so let's make it into its own module with a directory. We'll start by making a directory map, then we'll move map.rs into it and rename it mod, and then we'll take tile type out of mod.rs and put it into a new file, tiletype.rs. So one thing I'm thinking, by the way, is we have grass down here in the tile type. And I was thinking, I've seen the images below, and there's different, grass is not just like a single color, it's like commas and periods and like different things to make it look like grass, right? Different symbols, different glyphs. And I'm wondering if we're just going to do literally, I'm just guessing ahead, but we might literally do a random dice roll and just pick one of the glyphs. And then it'll just be random assortment of grass glyphs if it's a grass tile. Just a thought. We'll see how it goes, right? But that's a very simple way to go ahead and do it. So let's start the refactor here. I'm going to keep things like this for the moment, and then I'm going to expand the visuals shortly. So new folder, map, and we're going to take map and just slide it into the folder. Yep. Now, some things are probably going to be mad. We'll rename, there it is, to mod.rs. And we're going to need to go to main, and we'll say pub mod map. And we'll probably have to, no, we might be fine in here. Yeah, I think we might be fine. Oh, did it? Oh, I put it in here twice. Yeah, we already have map there. Never mind. We'll just do that. Yeah, it already was a module. My bad. I'm tired. Alrighty. So now, in this map directory, we're going to do tiletype.rs. And in here, we're going to need to do a mod. Like that. And then we're going to grab the tile type, yoink it out of here, and plop it in here. And there we go. Now we've expanded everything, it's gigantic. And we're gonna have it auto import these. And there we go. Now, hasn't gained us much yet, but we can now we can start supporting the various tile types. As we add functionality, you'll hopefully see why using a separate file makes it easier to find the relevant code. So one thing I find a little interesting is floor versus wood floor. I'm interested to see how that's going to change over time because we're going to have different types of caverns and stuff. So right now floor is very generic. But grass is a type of floor, wood floor is a type of floor, bridge is a type of floor. I mean, presumably you can walk over it. So floor is very generic, so we might even get rid of that at some point. So here we have all of our tile types now, at least for now. We added road, grass, shallow, deep, water, wood floor, and bridge. And this is only part of the picture because now we need to handle a bunch of grunt work. Can you enter tiles of that type? Do they block visibility? Do they have different costs for pathfinding and so on? We've also done a lot of spawn if it's a floor code in our map builders, but maybe that wasn't such a good idea. If you can have multiple floor types, right? Anyway, the current map.rs provides some of what we need in order to satisfy the base map trait for RLTK. We'll take a few functions to help, we'll make a few functions to help satisfy this requirement while keeping the functionality in one place. So we're going to make this tile walkable. And it's going to take a tile type and it's going to return a Boolean, whether it's walkable or not. And I don't like this TT. That, to me, that's not a good variable name, so I'm going to change that. So it's floor or tile type downstairs, or road, or grass, or shallow water, or wood floor, or bridge. Everything else is false. And there we go. So for any of those, we get a true. For anything else, we get a false. And that's a pretty easy place to set that. So now, later on, we can ask the question, is it a walkable tile? Now I'm going to say tile type. Because to me, that's better. So for this one, tile opaque. Is going to be the same kind of thing, right? But it's a different check. And if it's a wall, we return true. Otherwise, we return false. So we'll go back into mod.rs and we'll bring these things in. We're going to go here. We're going to do that right there. So now we have all the functions and everything. We could do the star, but that's how it's done in the tutorial. It's just including all three. So we'll go with that for now. And we're going to need to update some of our functions to use this functionality. So we determined a lot of the pathfinding with the blocked system. So we need to update populate blocked to handle the various types using the functions we just made. So for I tile and self tiles, blah, 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 that's all the same. But now instead of saying this here, we're going to say not tile walkable, and then pass in the tile. And that's all we have to do to change that. So now it's going to work with more tiles, which is good. We're going to also need to update our visibility determination code, which is opaque right here. So what we have right now is we're doing a check to say, is it opaque or view blocked? Well, no, we're actually saying, is it a wall? But we really want to say tile opaque self.tiles.index. Like that. And this is a weird one because on the tutorial, they're passing in an I32. I don't know why. And then they immediately say let IDXU equal IDX as U size. I think we commented on this once before, but I haven't touched this function since I pulled down that fresh copy after we got done with map generation algorithms. And that's how it was. I didn't make that change to U size, I don't believe. Maybe I did if Clippy was complaining, but I don't know. Either way. Yeah, so if the tile is opaque, or if the tile type is opaque, or it's blocked, like we already know it's blocked. So there we go. And that might be from like a door or something. So lastly, we're going to look at get available exits. This uses the blocked system to determine if an exit's possible. But so far, we've hard-coded all of our costs. When there's just a floor and a wall to choose from, it's a pretty easy choice. Once we start offering choices, we might want to encourage certain behaviors. It would certainly look more realistic if people preferred to travel on the road than the grass, and definitely more realistic if they avoid standing in shallow water unless they need to. So we'll build a cost function in tile type. So that's good stuff. This is something I talked about before. I've talked about this in my Dwarf Fortress streams as well. If you're using, for example, the A-star algorithm, but generally any pathfinding algorithm, you have some kind of cost. It's a heuristic that helps you determine what path makes more sense. So what is the shortest path from point A to point B? Is it a straight line? Well, if those straight lines are through deep water that you have to swim through, or you could just walk around the border of it in a quarter of the time because you're not spending all that extra time swimming, then you would actually want to walk around the border of that water, right? So you would have different costs for different types of tiles that you're moving through. And then the algorithm would take those costs into account when it's determining the path. And so your actual path is based on what is the total cost on this route. And then you kind of get to compare the costs, if that makes sense. So we're going to return an F32, which is our cost. And we're going to match on the tile type, and we're going to say road. .8 grass, not generation. 1.1 shallow water. 1.2 Am I the only one seeing a potential bug here already? This is the implementation from the tutorial, but what about deep water? Deep water gets a 1.0, but shallow water gets a 1.2? I don't know if I buy that. I would think you'd want shallow or deep water to be 1.5, unless you're not allowed to walk in it at all. But that, I don't know. I don't know if it's bug or just an oversight or what, but we're going to go along with it because often if you question the tutorial too early, you discover that there was actually a reason behind it and you didn't know it you didn't know it earlier, right? So now we're going to go back to get available exits here and we're going to update to use that. So what we're going to do is instead of 1.0 for this here, we're going to say tile cost. And where do we get TT from? Right after W here. Let tile type equal self.tiles IDX. As it's already a U size probably, isn't it? Yeah, it's already a U size. For some reason theirs is also taken in an I32. So now we pass in tile type right here. And oh, I didn't bring in tile cost. So for all the 1.0s, we're going to do that. Nothing else changes there. For the 1.45s, we're going to do the tile cost times 1.45. And that's all there is to it. So the tutorial text says we've replaced all costs of 1.0 with their call to tile cost, and then multiplied diagonals by 1.45 to encourage more natural looking movement. Yeah, and that's really the same behavior as before. Because if you can imagine, this was 1.0 times 1.45, so you can omit the 1.0. So it's really the same functionality as before, except now we have a variable tile cost, depending on what kind of tile. Love it. Also, oh no, there it is. Okay, I was looking at something different. All right, we're good. So now we're gonna have to fix the camera. We need to be able to render these tile types, so we'll open up camera.rs. So I'm gonna go in here, backspace, so Control-Shift-P to open the palette, and then you backspace and you just start typing camera, you hit enter, you got it. Awesome. Now, you see it's already mad because we're matching on the tile type somewhere, and we don't do an exhaustive match. So in get tile glyph, we're going to need to add a lot of new things in here. So we have floor. The next one I see here is wood floor, which looks like this. I'm going to copy these a little bit because I don't want to type them all. I don't want to type all the RGB named and RLTK 2CP437. I don't want to do all that. So next up is wall. And that should be the same as before. Downstairs, no difference. So now we get to the new stuff, which is going to be all of these. So let's just, look at them as we go. So bridge is going to be just a dot, but it's a chocolate color, which is the same as the wood floor, which is interesting. They're going to be hard to tell apart, but I guess they have different costs, right? Did bridge have a different cost? Actually, no, they're both 1.0. Well, that's fine either way. The way we spawn bridge is going to be different, so it'll make sense. We have road, which is the wavy thing. It's going to be gray. The tilde. I know what a tilde is. Why don't I call it a tilde? Because I'm thinking of it in terms of graphics, not a character. We have the quotation mark in here, the double quote for grass. Shallow water is the I forgot what you call that. It's like a partial equality or something. I don't even know. Why am I forgetting? Let me see. I gotta remember what that is. I feel stupid right now, I'm gonna be honest. Yeah, it is approximate. Two expressions are approximately equal. Okay, so for shallow and deep water, it's the same, but one like light and dark, basically. Cyan versus navy blue. That's all there is to that. If blood stains, visible tiles, so nothing else should change there. So now we're going to start building the town. We want to stop making maps randomly and instead start being a bit predictable in what we make. So when you start depth 1, you always get a town. In Map Builder's mod.rs, we'll make a new function. So I'm going to go ahead and just click into this manually back over here. And the reason I'm doing it is because there's a lot of things named mod.rs. So it's probably easier to just click in there. So many uses and stuff. You could definitely clean that up a little bit, but it's not that big of a deal in my opinion. All right, so we're going to make a new function, and we'll put it like right here. Doesn't matter, but we'll put it here. And of course, I have to scroll over because there's too much on one line to read. Even screwed up my thing over here a little bit. Okay. Now we're going to do a console log. Of the depth. And then we're going to say match new depth. And we're going to do that right there. Get a town builder, or any other depth that we get is a random builder. And of course we don't have town builder, but it's fine. So then we're going to come in here and we're going to add stuff to support that. We're going to do mod town. And then we're going to do use town builder. And now, of course, we don't have that, but we're going to have to make it. So let's pop into here. In map builders, new file, town.rs. It's already used, it's already declared. And here, so we're in good shape. Now we're going to need to actually put the town builder stuff. So we're going to get a builder chain. And let's see, pub fn level builder. And what are we going to do in here other than scroll over? So we're going to make our chain builder. We're going to start it with a town builder, which we don't have. We're going to get a random start position. We're going to do this area starting position new with the start X and start Y. We're going to put this distant exit and then chain. Distant exit's not being pulled in. And of course we don't have a town builder, so we're going to ignore that for now. Well, that's we're going to be doing that in a minute anyway. But the area starting position and distant exit are temporary to get us valid start and end points. The meat is the call to town builder. We haven't written it yet, so we'll work through step by step until we have a town we like. So here's an empty skeleton to start with. If that's what the tutorial says, then we're just going to copy it and get started with the skeleton. And yeah, that looks like it was a good idea. So we have a few things going on here. We have the initial map builder being brought in. We have our struct town builder. And we have, let's see. We have a new, which just makes a brand spanking new empty one. And then we have build rooms, which doesn't really do much. So we're calling a build rooms function that doesn't really do anything. Cool. Well, that's what we're going to write. So let's make a fishing town. We'll add some grass, water, and piers to the region. So we'll write the skeleton first. So we're going to need self.grassLayer with build data, self.water and piers, RNG with build data, make visible for screenshot, and there we go. Obviously, we don't have the functions yet, but we're kind of writing. It's not quite test-driven development, but it's a similar idea in that we say, here's what we want, and then we make it happy, right? So we're saying we're going to want to make grass, we're going to want to make water and piers, so let's do them as, let's go ahead and make our calls here, and then we can satisfy that. So that's a self dot, so we know we're going to need a functions that take mutable references to self. So we're going to come down here and say fn grass layer. Actually, it wouldn't necessarily have to be mutable. It depends on what you're doing. The way we're passing things around, because our town builder doesn't actually have any. Our town builder doesn't have any fields in it, so you might be able to get away without making it mutable. I'm not sure. So grass layer. Start with a nice layer of grass for t and build data.map.tiles.iter mute. Okay, I think that wasn't imported correctly. Yeah. And build data.take snapshot. Boom. So we're just literally going to set everything to grass, it looks like, as a way to start. And then we can modify different parts of the map to turn into water. So that's a simple one for now. We're going to take this one here, generate, and mute self. RNG is the nmute RLTK, blah, blah, blah. Build data is the nmute builder map. And we're not going to return anything, so we'll get rid of this here. But it saved me the effort. Okay, so there's going to be a lot more going on here. The text says, adding water is more interesting. We don't want it to be the same each time, but we want to keep the same basic structure. Here's the code. So we'll see how similar that structure is, but yeah, it could be interesting. $65, $535. There we are. Okay, so a 1D 65, 535 divided by 65, 535. And we are doing floats here, so we're not going to lose data. Okay. We're going to loop over the contents of the map here a little bit. So we have that n value that we compute. And then we have a vec of I32s called water width. So we're going to say let n water equals f32 sine n times 10.0 as I32 plus 14 plus RNG dot roll dice 1 6. And then we'll push that water width. So what's happening is we're doing this sine wave, and it's going to make the water literally go left to right a little bit. Like the width is going to change for each row of the map. So the idea is, like normally you'd see a sine wave going up and down, right? Like I'm doing my mouse here. It's going up and down like that. Well, imagine if we're doing it side to side a little bit. We're taking this sine value of n times 10. And then we're adding a value to it. And we're adding another value to it, which is from the RNG. So we're getting some width. And then that's going to be for each y in the map height. So for every row of the map, we get a different width, basically. And then here, we're actually going to set those tile types to be deep water. So we're basically going to go from the left side of the map all the way to that width and make them deep water. And then we're going to go from n water to n water plus 3 and make those, you might guess, shallow water. Because we're going from deep water to the coast, basically, so it's going to get shallow. So we close out that for loop, we close out that, and then we do build data dot take snapshot. That's all good, and now we want to add piers. Whoops, I'm on the wrong one. For here, we're gonna okay, we'll break it down in a moment because there's a lot of rolls and stuff happening, so we'll break it down all at once, I guess. All right, please format that. No? It's a little better now. Now that I had time to cool down, yeah, we're good. Let idx equal build data dot map dot xy index xy. Wood floor. Shouldn't it? Oh yeah, I guess wood floor works. Bridge would also kind of work. I don't know if we're going to treat bridges differently somehow. All right, so let's really try to break down what's going on here. So we're not using this value, so we're just looping from a 1d4 plus 6. So we're looping from 0 to a 1d4 plus 6. So we're going to have up to 6 piers. No, not up to 6. Up to 10 piers, right? Which is kind of a lot, but they're all going to be very narrow. They're 1 tile tall, I think. So then this y value is... yeah, we just randomly pick a a row from 1 to the map height minus 1. We're accounting for the border of the map. And then let's see this loop here. For x in 2 plus a 1d6, so a minimum of, it's 3 to 8, all the way up to water width. With that y value we just rolled, we're indexing into that to get the width of the water for our current row of the map. And then we're adding 4 to it. So we got to think about this a little bit more. So I'm trying to just come up with numbers or whatever. 2 plus. So one thing we know is that the water width is going to be wider than this. Like, we can pretty much guarantee that, because the water width up here is from n water, and we add 14 and we add this random dice roll to it. So this roll is never going to be larger than the water width. So then we loop from there to the water width plus a little bit more. And we're going actually notably 4 more, because here we went to the water width plus 3. Well, we're actually going plus 4 here, because that's going to put the pier 1 tile on the land and then some amount of tiles into the water. And it's basically, I think, 3 to 8 tiles into the water. If that's, yeah, that's what I calculated here. This random number here is between 3 and 8. So the piers are going to be varying lengths, basically. And we set all the tiles there to wood floor. So how do you come up with these numbers? Literally trial and error, a little bit of logic. I mean, we just broke down how it works. So if you follow how that works, you could have come up with the idea yourself. It's like, okay, well, we need to know where the water's at, like how far does the water go over? And since we tracked it with this vector here, we can index into it directly and use that value. So then we want to go a little bit to the left of it and then a little bit to the right of it. And again, we want to go 1 more than this, so it's on the land. Like, all the pieces are there. It's probably also a little bit of trial and error to decide how far out do you want the piers to go. This could have been a different roll. This could have been a different number that we add to the roll. There's a lot of things that you could kind of modify here to make it a little different. So just try different things if you're curious. Also, I was highlighting stuff in the browser just now by accident, but I think hopefully it was followable still. Here we go, back to the browser for real now. There's quite a bit going on here, so we'll step through. We make n equal to a random floating point number between 0 and 1 by rolling a 65,535 sided dice. Wouldn't it be nice if those existed? And dividing it by the maximum number. We make a new vector called water width. We'll store the number of water tiles on each row in here as we generate them. For each y row down the map, we make n water. This is the number of water tiles present. We start by taking the sine of n. We randomized it to give a random gradient. Sine waves are great. They give a nice predictable curve, and you can read anywhere along them to determine where the curve is. Since sine gives a number from -1 to 1, we multiply by 10 to give -10 to 10. We then add 14, guaranteeing between 4 and 24 tiles of water. To make it look jagged, we add a little bit of randomness also. We push this into the water width vector, storing it for later. We add 0.1 to n, progressing along the sine wave. Then we iterate from 0 to n water as x, and write deep water tiles to the position of each water tile. We go from n water to n water plus 3 to add some shallow water at the edge. Now, back to this number 1 here with the sine wave and all that. This is another one where you got to have a little bit of understanding about the math to understand what a sine wave is. But this is the kind of thing where you could Google it if you really. It's like, oh, how can I get a shape that looks like this? You know, and you Google around a little bit and it's like, oh, a sine does that. Maybe you don't have experience with trigonometry or anything. It's like, oh, a sine wave would work for that, right? So you might find that way, or if you have a vision in mind of what you want the coast to look like, you would recognize, oh, a sine wave would be good for what we're trying to do, a wavy coastline. And then the numbers that we're adding, like multiplying by 10 and stuff, and adding the randomness and all that, again, trial and error. You get something, it's like, oh, I'm not quite happy with that. Let's tweak a value here and there. A lot of game design really is trial and error. I know that sounds like a cop-out, like, you know, if you're looking at this and you expect that there's some magic to every number that was picked there, it's really not. It's not like, I just don't understand it, so I'm going to tell you trial and error. No, there really is a lot of trial and error going on in game design, just to get things to look correct. A way that I had a professor put it when I took a game design course was with like physics and stuff. He's like, it doesn't matter if it is right, it matters if it looks right. No one's going to care if the physics are actual correct Newtonian physics as long as it feels right. I said looks, the actual is it feels right, but feel and look go together in terms of gameplay. So anyway, we take a snapshot so you can watch the map progression. We iterate from 0 to 1d4 plus 6 to generate between 10 and 14 piers. We pick Y at random. We look up the water placement for that Y value and draw wooden floors staring at 2 plus 1d6 to water width Y plus 4, giving a pier that extends out into the water for some way and ends squarely on land. So we'll cargo run now, and we'll take a look and make sure it works. And while this is building, I'm going to scoot my chair back and take a look for something that I dropped. Oh, no, we have a problem. What is it called? Oh, but we have a couple problems here. Let me double check the tutorial text here. There is no town builder function being defined. I think we can work with it though. If it's gonna go the same way that I think it's gonna go, we're smart enough to do this. Let's find out. Oh, the town builder function would be in here. So it's not exactly what I thought it was going to be. All right, we have everything here. And it's going to be town builder new. We'll say let builder. I think we can get away with that. Let builder equal town builder new. And then we'll say builder dot build map. Right, that is our API. It's been a while since we've had to manually do one. We have level builder. Maybe that's all I need. Yeah, no, we just need level builder. Okay. Maybe let's get rid of town builder here and say town builder level. No, it's not public. Oh, it's not town builder, it's town. That's why. There we go. Okay. And now we're not using level builder. Oh, wait. Yeah, we have level builder in 2 places. So in main, we have random builder. Whoops. Hey there, Tusk. How's it going? Ah! Don't, I almost did the wrong thing. Let's just force it to level builder here in main. All right, now that's building. Let me check for that thing I dropped. Oh, we got a crash. Hang on. Why'd you do that, Tusk? Couldn't find it, but I'll look. I'll look more later. Depth of 1. No valid floors to start on. We're at area starting points. All right, we are having some issues. What is going on? There's a bunch of stuff missing, which is frustrating. Let's take another look here and scroll up a little bit. I was told in town.rs so first, level builder in our mod does this here. It calls the town builder and everything, right? And then it says use town builder, lowercase town builder. There is no lowercase town builder function that we've created, but we did make level builder inside of town.rs. So that's what I'm calling. And it looks like chains start with town builder new. So let's come back over here. Start with town builder new. And then what we're not doing is building the rooms. Right? So should it not be chain.build build map? But then what is build data? Where did we get build data from? So if we go here, simple map builder. Sorry, it's been a while. Builder chain. I'm gonna go back to main. Builder.build map. No, that should be okay. Because it calls them in order. it calls each builder in order. Yeah, we don't build it here. So it should start with town builder new and build map on that town builder. And then do the starting position. But you know what it might be? We haven't set up random start position. Which one's crashing it? Area starting points. Available floors. If tile type is floor, that's not what we want. What was it called? Tile walkable. Tile type. There we go. Not in the tutorial. It says we could cargo run. They're making me debug. There we go. There's a map. Looked really cool, too. I can't move into the water. Oh, because it's not walkable. Yeah, that's why we didn't need to worry about the deep water. Look at that, though. That's so cool. We got our little piers and stuff. We got our grass. We got our shoreline. Let's run it again. Watch, because it's going to be very quick, but watch. And you'll see the whole map pop in. Boom. That's so cool. One more time. Love it. One more time again. Love it. Alrighty. So we got our basic map starting here. We can take a look here on the tutorial page now and see what it looks like. So there were a couple issues there that we had to take care of where we were crashing. If you cargo run, you'll see a map like this now. There was no indication that we needed to change those in the tutorial, so that I would call that an oversight of the tutorial. Unless I somehow missed it, I would call that an oversight. Which is okay, things happen, but it's unfortunate. You see, we were able to figure it out. So adding town walls, gravel, and a road. Now that we have some terrain, we should add some initial outline to the town. We'll extend the build function with another function call. So we're going to do this here, let mute available building tiles and wall gap and stuff. I'm going to just copy that one because it's a little bit chunky. So the build, I guess we're going to add this right here. Town walls. We'll just put it right after the water and piers. And then we need to make the town walls function. So let's go ahead and click on this and have it generate. And everything should probably be okay. They're taking a mutable reference to self. I don't think it needs to be, but we'll see. Oh, and this actually does return something. Right, of course it does. We just saw that. Because we're assigning things. So I need to get down here and say available. And we're going to return that, so we need to make those. So we're going to make a new hash set there. And it's going to be smart enough to figure out what it is because we're returning it. So we're going to do a random roll for the wall gap y, which is just going to be how tall the gap is, right? All right, so we have our hash set, we have our wall gap y. That's all we need. Now we're done. No, we're not. Let's actually do the work. For y in 1 to build data.height minus 2. If not, y greater than wall gap y minus 4, and y is less than wall gap y plus 4. Just gonna hammer through a lot of this because it's a lot, and we'll break it down afterward. There's too many indices and stuff going on here. Very cumbersome. We don't have gravel yet, so that's going to be mad. Okay, that's a lot of stuff happening. Let's try to break this bad boy down. So for y in 1 to the height of the map, basically, so for each row of the map, y, if it's greater than the wall gap minus 4 and less than the wall gap plus 4, no, if it's not, rather, if it's not greater or less than the wall gap plus 4, then we get the index at x of 30. So we're hard coding where we're at. We're hard coding 30. Then build data.map.tiles. So we're going to set that to a wall, and then we're going to set the index next to it to a floor. And then we're going to get the right index we're building another wall on the right of the map. So let index here is the left wall. Let index right is the right wall. I see. Okay. And then we loop over the rest of the X's, 31 over to that right wall. And we set that to gravel. So we make that a gravel index, we're calling it. And then we set its tile type to gravel. And then as long as it's within the correct Y value as well, we insert that in the available building tiles. Now back to this, if we're not within the correct rows, as was determined up here, then we set that to be a road. So there's some tiles that are going to be roads. So the road's going to run like between, it's going to run through the wall gap. That's what I'm seeing here. Now we don't have gravel yet. I'm guessing we should be able to walk on gravel. But is it ever mentioned? No. Literally the tutorial just added gravel without telling us anything about it. So I'm going to make some assumptions. Because what else can I do, right? So this sucks because now I have to remember everywhere to add it. So we have gravel there. I'm going to assume gravel is walkable. So we're going to put gravel there. And I'm going to assume that the cost is, I'm going to say 1.0 is fine. No, I'm going to say gravel is 1.1 as well. Gravel and grass are the same. I'm just guessing. You know, I have no clue. I think they're using a semicolon. So if we have tile type gravel, does it really matter that much? Probably not, but I will just put a gray. It's a different gray though. It's like a light gray, maybe. Okay, so now that that's in place, let's read the breakdown of what we just did. And let's actually cargo run it first, and then we'll break down what's happening. This tutorial is getting really just hands-off at this point, which is fine if they kind of said, you know, if it said that that was going to go that route, but it kind of just is doing things without telling us. Oh, I got a bad spawn. And we got our stairs there, but we don't need them. So this is our road here. And then up here is all the gravel where we're going to be building things. Alrighty. So you see we've got like this place is walled in. And then again, that's the wall gap. So let's click over to the tutorial now and read the description of everything we just did. So we're making a hash set called available building tiles. We'll be returning it so that other functions can use it. We set wall gap y to be a random y location on the map between 6 and map.height -8. We're going to use this for the location of the road that runs through the town and gates in the city walls. We iterate the y-axis on the map, skipping the very top and bottom. If y is outside of the wall gap, 8 tiles centered on wall gap Y. We'll draw a wall tile at location 30Y and a road at 29Y. This gives a wall after the shore and a clear gap in front of it. Clearly they have lawn management employees. We also draw a wall at the far east of the map. We'll fill the intervening area with gravel. For tiles that gained gravel, we'll add them to the available building tiles set. If it is in the gap, we draw a road. Lastly, we fill rows 1 and height -2 with walls between 30 and width -2. You cargo run, you have the outline of a town, which is what we just saw on mine, but we can see a full shot of it here. Pretty cool. Okay. Next up, adding some buildings. A town without buildings is both rather pointless and rather unusual, so let's add some. We'll add another call to the builder function, this time passing available building tiles structure we created. Wouldn't call it a structure, but it's a data type. It's a hash set. So let's just copy this. That's going to be our skeleton, and then we'll work with that. And I'll probably copy this as well, just so I don't have to deal with it. So let's go to our town.rs here, and we'll go right after the building tiles thing is created, and let mute buildings equals self.buildings and all this good stuff. So we're going to come down here. And here's the skeleton of buildings, where it takes in the RNG, the build data are available building tiles, and it returns a vector of tuples, each containing 4 I32s. My guess is that's going to be the outline of the building, the 4. It's, well, not the 4, but it's going to be maybe the upper left and bottom right corners, maybe? We will find out. My drink is empty. All right, so now I'm just going to say let mute buildings equal vac new, because later on we're going to return buildings. Whoops. And it's smart enough to figure out that it has to be that because that's what we're returning. And I put this in the wrong place by accident, so let's slap it in up here, and that's better. Okay, now we make our buildings vector, and let mute end buildings equals 0. And while there are less than 12 buildings, we're going to roll our dice. 1 build data dot map dot width -32. Plus 30. So we're doing our roll, and then we're doing an offset with the plus 30. And that offset is already determined based on how we've built the rest of the map. It's kind of, that seems like a magic number maybe, but no, it's hard-coded because we know how wide we're making the shore. We know the wall is hard-coded at 30. Right, so we know a lot of things about the map. Okay, so now we have a building width and a building height. I'm guessing that's what BW and BH mean. And we're going to say let mute possible equal true. I already don't like this. But we'll roll with it for now. I'd rather do stuff with iterators and all that, but whatever, we'll roll with it. So I want to actually take a moment to elaborate on something when I talk about using iterators. This is a potential example where it may not be as helpful in terms of performance, but I was actually talking to somebody about this morning. They were talking about bounds checks in Rust. They sent me an article, and it was about removing bounds checks, but not going into unsafe territory. And I immediately responded with, why would you do that? And I was already going and grabbing the article that I showed on one of these coding streams about how bounds checks are very negligible in many cases. I'm not going to say every case. There's probably cases where it's not negligible. And in fact, some of those cases I think were mentioned in that article that I'm referring to. Things like auto vectorization or SIMD, single instruction multiple data. In cases like that, you're going to get huge speed ups if you can allow that to happen, right? So bounds checks may cause some issues in that, but they also may not. And in fact, in many cases, they won't. But that is one case where it could actually really be helpful to not be doing bounds checks, right? So the point is, before I could even, I had the article within 20 seconds and I'm sending it, but they just responded performance. And that's why I was sending the article, because I'm like, we see performance is not necessarily going to be impacted in any significant way by doing bounds checks. And we were talking about it a little bit, and I was saying how one of my big philosophies that I've been holding to and I've mentioned multiple times, sometimes good enough is good enough. Optimizing something for the sake of optimizing it doesn't make sense. Now, granted, you should think about your design early on to make sure you have a somewhat decent design, but in many cases, it may be hard to tell what areas are really going to impact your performance until you do some benchmarking, right? Until you actually see a bottleneck somewhere. So I wouldn't say, not to try to have a good design, but I would also say maybe don't worry about some things like performance in a lot of cases until you find out that it's really going to be an issue. You also wouldn't want to have to rewrite thousands of lines of code or something because you wrote bad code. So there is a middle ground here, right? That's what I'm trying to get across. Now, why am I going down this tangent? Because I'm not really linking it back to what we're talking about here. Iterators. The example I brought up was something that I did a while back. It was a combinatorial problem that I was working on, and it was from a game. And basically, you have these like 2 rows of 8 seats, and you're trying to seat different creatures in each seat. Creatures have to have at least one thing in common with every neighbor. So the 2 rows are adjacent to each other. So something can have a neighbor to the left, right, and above or below, right? Now, if it's on the edge, then it gets to not have neighbors on either side. If it's on the left edge, it can't have neighbors on the left. If it's on the right edge, it can't have neighbors on the right. But basically, they have like 4 different body parts, or 5. They have feet, nose, eyes, and hair. So I guess 4. And each one of those, again, there has to be at least one thing in common with the neighbor. So it's a combinatorial problem. And I was curious, I wrote some code to solve that. And I did it in 2 different ways. I did it with iterators, and I did it with a for loop and conditionals. So the iterators, the game was called the old name was Logical Journey of the Zumbinis, and the new name is just Zumbinis. But I had like my vector of Zumbinis. Something like that. We'll just say that for brevity. Just imagine that there's 16 of them in there. And then it was something like zumbinis.iter.filter validate row. And then it was like that. This is a huge tangent, but if I can type the ampersand, geez. And then we do another filter from 8 to 16. And then we do another filter, validate columns. And I don't remember exactly how I set that one up. But basically, we validate the columns, and then I think I just did .next to get the first, to get the first thing, and we could do an unwrap if we want. But basically, this is the idea, right? This is the iterator version. So I had to have a function called validate row, and then I could pass it slices, which represent the first and second row, and then validate columns. It was basically a for loop that just went from 0 to 8, and then it checked 0, like it checked if I is our loop counter from 0 to 8, then you add 8 to that. So you're checking 0 and 8, 1 and 9, 2 and 10, and so on, right? And that's checking the rows, the neighbors from top and bottom with each other, if that makes sense, right? So that's basically the algorithm. And what we could do here, it's very simple, pretty easy to read. We could also do something like this well, how did I do it again? I had combinations, actually. That's the one thing I'm leaving out. So it's iter dot combination 16, and that comes from iter tools. It might not be called combination. It might be because there's permutations and there's combinations. But the function might just be called combinations. It might be something slightly different. It doesn't matter though, right? So then that's actually more like what I actually would have had. And then I'm not doing the proper syntax here. So what it's really going to look like is combo. And then this would be combo. And then same thing here. And we're just going to do ... here. There we go. That's more accurate, but it's not perfect still. So then what's the equivalent here for combo in Zumbinis .iter .combinations 16? And then we have the combo here. So then it would be like if not validate row and combo 0 to 8, continue. And we do the same thing for the second row, right? So it'd be 8 to 16. And then ... And then if we get to the end and we find one that's valid, we can break. We'll save it to a variable or something and then break. So these do the same thing, right? One of them, we get the iterator and we filter. So we validate the first row, we validate the second row, then we validate the columns, and then we get the first thing. So what we've really done at that point, that iterator is every possible solution, but we're just getting the first solution. So the equivalent here is we go through, and if it's not a valid row, we continue because we're done with this. If it's not a valid second row, we continue. If the columns are not valid, we would continue. And then if we made it through all 3 conditionals, then we found a solution. Same logic, right? What I found is that it took like minutes, like more than 10 minutes, I think, to run this for loop version. Now, maybe I could have done something better. You know how long it took to run this? Less than a second. I didn't look at the assembly or anything, right? But what I have to imagine is that there is some kind of auto vectorization or something going on here that's allowing this to be extremely optimized compared to the for loop thing. But I feel like I'm doing things that should optimize this somewhat, right? I'm not continuing, well, no pun intended, I am hitting continue, but what I mean is I'm not going through the entire loop here if I find a spot where it's not valid. I just go to the next one. I throw it away once we find out, oh, this isn't valid. Let's move on to the next, right? Despite that, this was so much slower than using the iterators. Like I'm talking legitimately minutes. I went and like brushed my teeth and come back and it still wasn't done when I was running the for loop. So when I talk about something here where I'm like, we're setting a variable to be true. This is to bring it back now after like 10 minutes of writing pseudocode and stuff here. When I talk about like, man, I would prefer to use iterators and not make this like this possible variable. In this case, it's going to be a little funky because we have this double for loop going on here. It's still doable, but because we have this double for loop and everything going on here, it's going to be a little bit more funky. But when I start talking about things like I'd rather just use an iterator and do a .any or .all or something if we're going to be checking if something's possible. When I say that, that's kind of an idea why I'm interested in that, because it gets us around, one, we don't have to worry about indexing as much because that iterators kind of handle that for us. And two, they can actually be much, much more performant because the compiler, the kind of simple way I guess I would put is the compiler knows what those iterators are doing, and maybe the way you write your code is harder to optimize. Compilers are smart. LLVM is smart. But it's smarter when you're working with these iterators than when you're making kind of arbitrary loop constraints, if that makes sense. So that's a big roundabout way of just providing a real example of why it is that I like I always mention it. I'd rather do it this way. I'd rather do it that way. I always say this feels very C-like. And that's okay if you're writing C, but we're not writing C. We have the tools available, so I'd prefer to use the tools that we have, right? So anyway, let's continue on now. All right, so what are we doing here first? We get our building X, Y, and width and height. And we're checking to see if it's possible to build something. So we're going to say for Y in the building Y values, so from BY to the height of the building, and the same for the width values. We're basically looping over all the possible tiles of this building. And the main thing we're doing is we're doing two checks. The first one is a simple check. If it's out of bounds, we can't build it, so possible is false. Otherwise, we get the index, and if it's not in available building tiles, then possible is false. That's all we're checking so far. So pretty simple. Then now we have a value of what possible is. We know whether it is possible or not. So if possible, n buildings plus equal 1. Now I'm hoping we're going to remove, I was going to say we're possibly going to have overlap, but I'm guessing we're going to remove these from the available building tiles. Is it a mutable reference? It is, so we're probably going to remove them from the available building tiles. And that way we won't have overlap. So we're going to loop over the tiles again. We're going to put wood floor here. Available building tiles dot remove index. And we're going to do a few more here. And I don't feel like typing them, if I'm being honest. So let's just look at what we're removing here. So, because I'm not 100% sure yet why we're removing the surrounding tiles. We remove the index, which we changed to wood floor, but we also remove the tile, the four cardinal directions, right? Up, down, left, and right. Not sure about that yet. Oh, you know, You know what it might be? It might be a really goofy way of building the border. I don't know. Building the wall around the side of the house. That might be a way to just make sure we leave room for the wall. Rather than building a secondary loop that specifically puts the walls in. Well, we're going to have to do that anyway, though. No? I don't agree with that. We'll see. We'll get the explanation at some point, right? Now we're going to outline buildings, which I think is what I was just describing. We're going to clone the map. Get the build data height. We're going to loop over that. We're going to loop over the build data dot width. But we're offsetting that by 32. Taking into account where the walls and stuff start in our map. And if the tile type is a wood floor, neighbors is 0, and then we're going to calculate some neighbors. I don't feel like doing that. This is code we've done many times before, so we can break it down, but it's literally what we have up here. Index +1, index -1, index plus the width, and index minus the width. It's the same thing, but in this case, we're checking for neighbors that are not wood floor. And if we have more than one neighbor that's not a wood floor, then this is now a wall. Because what we do know is if all of the neighbors are a wood floor, we're like in the center of the building, right? But if we're on the edge, then we're going to have gravel or something. So that's what we're just doing here. We're counting how many tiles are not wood floor, and that tells us, oh, these are now the walls of the building, right? So if neighbors is greater than 0, we set it to a wall. And then down here, build data.map equal map clone. And we'll take a snapshot. We're good to go. So let's see if I can run this. If I didn't make any mistakes. Gotta watch quick. I know this first one's gonna pop up because it's still compiling. You don't know when to expect it. But it should be up right about now. Let's see. Boom, we got buildings. Boom, we got walls. We had no doors, but boom, we got walls. Look at how cool that is. We got us a little town. This is really cool. Seeing the way this is coming together now after so many weeks of laying the foundations, no pun intended. Look at this. We got our buildings here. We got us a town, man. And we can walk around in circles until we're hungry. I like how we do have like a couple things here at the bottom. We have a couple buildings that made it down here. Alrighty. So now let's go back to the text and read the description of the algorithm. I think I maybe broke everything down well enough as we were going, hopefully. Maybe not. But basically, while there's less than 12 buildings, we get a width, height, all that stuff. We get our description of how big the building is. We make sure that it's not out of bounds, and we make sure that all the tiles are considered available building tiles. And if it is valid, then we push that description, the X, Y, width, and height of the building into our buildings vector that we're keeping track of. And then we loop over and set all the tiles to wood floor. And then we also remove the surrounding tiles from available building tiles. Then we build the walls by counting the neighbors of each tile, and if there are more than 0 neighbors, then there needs to be a wall. Neighbors being tiles that are not wood floor. Those are valid neighbors for this purpose. So let's read their description. We make a vector of tuples, each containing 4 integers. These are the building's x, y coordinates along with its size in each dimension. We make a variable n buildings to store how many we've placed in loop until we have 12. For each building, we pick a random x and y position and a random width and height for the building. We set possible to true and then loop over every tile in the candidate building location. If it isn't in the available building tiles set, we set possible to false. If possible is still true, we again loop over every tile, setting to be a wooden floor. We then remove that tile and all 4 surrounding tiles from the available building tiles list, ensuring a gap between buildings. So my intuition on that and just deducing it, that was correct. Making sure they're not like on each other, basically. We also increment n buildings and add the building to a list of completed buildings. Now we have 12 buildings. We take a copy of the map. We loop over every tile in the town part of the map. It's weird wording there, but loop over every tile in the town part of the map. For each tile, we count the number of neighboring tiles that aren't a wooden floor in all 4 directions. If the neighboring tile counts greater than 0, then we can place a wall here because it must be the edge of a building. We write to our copy of the map so as not to influence the check on subsequent tiles, otherwise we'll have buildings replaced with walls. We put the copy back into our map. We return out our list of placed buildings. If you cargo run, you'll see that we now have buildings. Yeah, we just did that. So now we're going to add some doors. The buildings are great, but there are no doors, so you can't ever enter or exit them, so we should fix that. Extend the builder function with another call. So we're going to say let doors, and this is nice because we actually have our list of buildings already. So we can pass that in, and we know where our wall gap is at. So I think we're going to be using that to make sure our doors face the road and stuff. I've looked ahead and I've seen how that town looked, so that's my guess of how we're going to be using it. But I don't 100% know. I haven't read the code, I just saw what it looked like. So we're going to put this add doors function here. It takes our RNG, it takes our build data, our builder map, it takes our buildings vector that we just made, and it takes our wall gap, and it returns a vac usize. So let mute doors equal vac new, and we'll return doors at the end. Now, one other thing I did see is that we're going to be building paths to the road. So the reason we're returning the doors, the vector of usizes, those are probably the indices of where the doors are at, and we're probably going to use that to make the little paths. For building in buildings dot iter let door x equal building dot 0 plus 1 plus RNG dot roll dice. It's going to be a 1D building dot 2 minus 3. We're going to have to just figure out what that is. So what is building dot 2, 0, 1, 2. That's our, where'd it go? That's our width. So we get our width minus 3. So it's anywhere from basically the left of the building. Oh no, wait, I'm on the wrong thing. Door X equal building.0 is X. So that's our width, right? No, that's not our width. That's our X location plus 1. So now we're inside the building. Or we're within the walls, rather. And then we roll a dice, a 1D width minus 3. So if the width is 10, we're now at 0, we're at 1. And this would be 10 minus 3 would be 7. So it would be anywhere from 1 to 8 if we had like a width of 10, for instance. If I did that right. Basically, we're picking a random spot across the width of the door of where we're going to put, the width of the building of where we're going to put the door. Now this here, building.1 is our Y, plus the height of the building over 2. Right, because the height is the last, is dot 3. Yeah. So we're going just into the center of the building, basically. And that's CY. Maybe that means center Y. I don't like that variable name. I don't know what CY means, so I'm figuring it out. I think that means center Y. So if CY is greater than wall gap Y, door on the north wall, and I called this. And finally, we're doing a nice conditional like this. Instead of setting let index semicolon and then doing the if cy blah 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 and then doing idx equal this and idx equal that, I prefer this style. Let index equal if something and then return stuff from the if. So we get, if it's on the north wall, we could just get the y value, the by value that we put in. If it's on the south wall, which is our else clause here, then it's going to be the y value plus the height minus 1, just to take care of that off by 1 issue there. So now we should know where the door is going to be at. Whoa! Thank you, Z-Sauce, for that. I appreciate it. Appreciate the follow. How you doing? Okay. So we figure out where we want to put the door. And right now we're actually just setting it to a floor because the door, if you recall, is actually an entity from the ECS. So this goes into our spawn list and we know what door means in our spawn list. So that's going to actually give it all the correct components and everything to be an operable door. So if we did everything right, we'll walk through this one more time after it runs. Well, I saw the cutouts. Definitely saw the cutouts, so it looked good. We should have buildings on both sides too. And boom, we could see inside. Beautiful. Looks like the wall got a little... Yeah, it looks like they got a little funky near the town wall, so we'll probably have to double check that at some point. I might even know what did that. We'll double check that if it's not addressed. I don't want to jump too far ahead. I don't think I need to walk in every building, do I? But it's so satisfying. They work now. We could generate another one. Whoops. I'll have to relaunch it, actually. Yeah, I think our check over here... I have to take another look at it and think about it, but... I think there was an issue with this in correctly setting the walls. And if a building spawns right next to the town wall, it leaves a bit of a gap. So again, we'll keep that in our back pocket and maybe check it later. But it may be addressed. So like I said, I don't want to jump ahead. So we'll break down the function here now. Quite simple, but we'll step through it. We make a vector of door locations. For each building in our buildings list, we'll set door X to a random point along the building's horizontal side, not including the corners. We'll get CY to be the center of the building. And if it's greater than the wall gap Y, that's where the road is at, then we place the door's Y coordinate on the north of the building. So the door is going to be facing the road. So if it's actually south of the road, then the door is going to be on the north of the building. If the building is north of the road, the door is going to be on the south of the building. So then we'll set the door tile to be a floor, and we add a door to the spawn list, and we add the door to the door's vector, and we return it because we're going to be using it. And again, just having looked ahead, my intuition, and there it is, paths to doors. We have the index of where the doors are going to be located, so we can use that to path to the road now. And I think they're using A star here, so we get to use it real quick. But we're not like implementing A star. So it'd be nice to decorate the gravel with some paths to the various doors in the town. It makes sense, even wear and tear from walking to/from the buildings will erode a path. So we add another call to the builder function in the self.addPaths. So I'm going to pull that in, and then we're going to just bring in the signature of the function the lazy way. Save typing. Although it's a pretty short one, it's not as long as some of the other ones. All right, we have our add paths here. This takes mutable reference to self. It takes our build data, so our builder map, and it takes the doors vector that we just built out. And good news here, we are using a slice. So I've talked about this before. It is valid to say vec usize. You could take a reference to a vec usize. But it is kind of better to take the slice here because it's actually more flexible. You could do more with it. So you could then pass a vector in by just putting like amp my vec, ampersand my vec. You could pass a vector in like that. That gives you the slice that you need, but you also have more flexibility in other things you can do with it. It's kind of like what I talked about before, where if you have the option, if you're like going to take in strings, you should take in a string slice, because if you have a let my string equal test.toString, so we have a big S string here, and you could say let test equal test. You have a string slice here, and then you say fn, we'll put it out here. And we'll say input takes a string slice, does something. then we could say test my string and test. Both of these should work unless I did something goofy. What did I, oh right, I should use a different name. That's probably not helpful, is it? There we go. Now it's not mad. See, it starts screaming at me and you think I'm wrong. No. The point being that we can have simply putting the reference here on my string, the big S string, allows us to pass that in as a string slice, ampersand str, just the same as we could pass this in here. So rather than storing the string slice in a variable like that, we can even just pass it in as a string literal. So that's kind of the preferred way to take strings in, if possible, because you can kind of use both types of strings almost interchangeably there. Similar to the slice here. This is more flexible. It gives you more options. So let's go ahead and add our paths now. And this is going to be the main thing we're going to do to wrap this session up. So let's go. And this one's actually not returning anything. So we're done doing our returns for now. So we don't have to worry about anything. I don't have to worry about it getting mad or anything until I get to the end. Quick question, why did I have test.toString? Because I was making a big S string. I mean, you see, we have a big S string here. I was showing both types. Yeah. We lost the function now, but I was showing that here, when you use the big S string, if you just put the reference in front of it, you could do the string literal like this, or you could actually have the ampersand str saved off, or you could do the big S string and just reference it. You could pass like all three types into the same function. So instead of toString, I mean, again, just to get the big S string, I could have also done string from. You also do it that way. All right. All right, we're going to loop over basically the entire map. I'll address that a little bit more in a minute, but I will say I definitely think it's something worth looking into. I think it's a lot of fun. I'm going to elaborate a little bit here in a minute. Some of the benefits, I think. It's not some of the typical stuff that you hear either. Everyone likes to talk about, they like to talk about the safety and stuff and performance, and there is that, but there's more to it than that for me. That's funny. You just said the main thing you hear is safety and performance, and that's literally like I just said. There is that, but there's more to it. Those are the first two things I mentioned, yeah. I just think that's too simplistic of a view for the language. Now, okay, we're going to get our iterator over the doors here. So let's break down the first part real quick. So we're making our roads vector. We're going to loop over the map, and we're just basically getting the indices of the tiles that are roads and just pushing that. So we are keeping track of all the road tiles in the map. Now, I'm not sure why we don't do this in a little bit of a cleaner way. Am I missing something here for, idx in build data.map.tiles.iter, and then we'd filter that. And then we would say, yeah. Tile type road. Whoops, I need to enumerate as well. Yeah, and I don't know why I put the for loop. I was reading the top thing, it threw me off. So .iter.enumerate. And then there's going to be oh, it's not index anymore though, it's tile. There we go. I kind of jacked it up a little bit, but I feel like that should work, and I'm going to hold that in my back pocket and try that. All right, so for the door index in doors.iter, so this is a familiar construct we've seen a lot of times where we have a vector of tuples of U sizes and F32s. So if you've been following along with this, that should be a giveaway of what we're doing here. We're probably storing indices and a distance, the F32 being the distance. And this is probably going to be the height, or the, not the height, the, we're doing the divide and mod technique, so. Yeah, so we're doing the divide and mod technique, so as a reminder, just pointing it out, that we are doing a 1D array, or it's really a vector. We're treating the 1D vector, that is our map. If we go to map real quick, our tiles is just a single vector here. It's not a vector of vectors or anything. So we're treating that as a 2D, so we have to do tricks like the divide and mod. And that's also why we have the map XY index that you see me using all the time. So we convert it to a RLTK point, the index that we're looking at. We're going to do a distance algorithm with Pythagoras squared. Distance 2D, that's another pretty familiar one because we've done it a lot. Oh, whoops. There we go. It's a bit beefy there, and I typoed RLTK. So we're making a point there. So this is the road. I don't really like R, so I'm going to say road. For road in roads.iter. So we're going to get the roads index, which is, it's already a U size, so that's fine. And then we're going to convert that index into map coordinates, basically, into a point. So we can use that point to get the actual distance, which is what we're doing here with the distance algorithm. That's our nearest roads dot push. Now we're going to sort it. We're going to sort by A, B. By the way, what do you said you never programmed in Rust, but what do you program in? What kind of stuff do you do? Partial compare and B.1. Sort by, simple enough. We're going closest to furthest because we're doing A and then B. We would do B and then A if we were gonna flip it the other way around, go longest to shortest. So we're just trying to find out the shortest road here. And then because we've sorted them, we can just get the first thing in our vector. Oh, whoops, I already did that. Let path equal RLTK A star search. And we're gonna need the door index, destination, and build data.map. This gets us back a navigation path type, which holds the results of an A-star navigation query. Destination is the index of the target tile. Success is true if it reached the target, false otherwise. So navigation path actually has a success thing in it, it seems like. So we'll say if path.success. And then we have these steps that we can iterate over, which is going to be each tile, basically, of the map. So we're just going to get each one of those tiles, call it index. Set those to roads. And then push that in there. There we have it. So let's run through that again. We usually program in C, C++. I have never heard of System Verilog. My first language was C in university, and then they moved from C into C++. And that was all we formally learned. No, well, I think assembly was a required course, but it was a one semester thing. So C and then C++ and then assembly. Anything else was incidental. You either learned it on your own or you took a course which was like, we're going to do this in this course. So like I took a programming languages course where we did Haskell, Prolog, Java 8, Scala, Swift. I think that was it. And then I did a lot of AI stuff, so we learned Lisp in there. I'm trying to think if I learned anything else like in any courses in university. That might have been it. Almost everything I did, I just kind of figured out Python at some point because it's so easy. But almost everything I did was C++ or Lisp in university. All right, so we can try running this. We'll break it down real quick. So we're basically just collecting all the roads, all the indices that are roads. And then we populate blocked. And we have to do that because we added a bunch of walls and stuff to the map. And we're about to do a pathfinding algorithm. So we need to make sure that it knows which tiles are blocked. We go through each door, which is door index. We find all the nearest roads. And we use the, basically for each road tile, for each road tile, we calculate the distance using the Pythagoras squared distance algorithm. We collect all those into that nearest roads vector, and then we sort them. So we're sorting by the F32 value, which is the actual distance. And then we get the closest one, because now that it's sorted, we get the first, 0 index. And that's where we're going to path to. So we do an A star search to that index. And if it was successful, then we just iterate through all the steps of that path and push those into the roads vector that we're maintaining. So then we can, what's interesting about that is because we use that up here, it is possible that we're going to have roads branching onto other roads, which is going to look really cool. It's not necessarily going to be the big road running through the middle of the city. You could have something pathing to another nearby road, which will make it look a little more organic. So if I didn't make any mistakes, we should be able to run this. There we go. We actually had that happen. They put me way out on the pier. We actually had one branch. There were a lot of them that were really close to the actual road here, so the paths aren't very long. But over here, I noticed this here, it's a little hard to see, but this goes diagonally to this door. And then down here to where this is at. And then these go over this way. We have a road moving up this way, straight up. So not everything just paths directly to the main big road. Get another look here. Yeah, it's pretty cool. I like it. So I want to do this real quick. Rather than this construct here, did I do this correctly? What I actually want to do is break apart the tuples, though. I don't like calling it tile. Yeah, we're still good. So let me break apart these tuples real quick. And it's going to be index and tile. We can get rid of the, oops. We can get rid of the dot one there. Yeah, no, we do need that. Oh, I see what I missed. There we go, and now we need to double deref that. I could put a ref there, but it's fine. We don't need to worry about it. And then here, I'm going to just copy this. Instead of tile, like that, we're going to have index. We don't need the tile there. And there we go. That should be good to go. Probably faster. Not that it matters in this case, but it probably is faster. Had a lot of really samey ones there. There we go. That looks pretty cool. All right, so let me wrap up. I'll answer your question in a moment. Well, I'll do this and then I'll address it. I'll just read this one section here and then I'll address it and then we'll go to the next section after. So just to recap what's happening there, because I gave my recap. Here we have this as well. We start by making a roads vector, storing the map indices of every road tile on the map. We gather it by quickly scanning the map and adding matching tiles to the list. Then we iterate through all the doors we placed. So we make another vector, nearest roads, containing an index and a float. We add each road with its index and the calculated distance of the door. We sort the nearest road's vector by the distances, ensuring that that element 0 will be the closest. Not that we're doing this for each door. If the nearest road is one we've added to another door, it will choose that one. We call RLTK's A-star pathing to find a route from the door to the nearest road. We iterate the path, writing a road tile at each location on the route. We also add it to the road's vector, so it will influence future paths. If you cargo run now, you see a pretty decent start for a town. We just saw that. We get a good look at it here with the whole map, though. Not worrying about any FOV or anything, right? Why is it probably faster, though? I'm not going to dismiss, so don't think I'm dismissing. But the start of this is I actually went on like a 10-minute detour earlier giving an example of something that I've done in the past where it really showed the power of iterators in Rust. I don't want to go over that entire example again, but it is like a good example. So I'm not trying to dismiss. I'm going to just try to make this a quicker version or something. Basically, Rust iterators are very good. LLVM is really good at optimizing those iterators. And so the example I saw was, or not saw, is something I did. It was a combinatorial problem, right? Where I had to figure out different combinations of things that fit within some valid constraints. So I had something where I could loop through it, and it was 3 different main validations I had to do. I had to validate the top row, I had to validate the bottom row, and then I had to validate all the columns. So there were 3 basic sets of validations I needed to do. If I do the iterators, it's something like my vec.iter, and then I had the combinations. And then you filter it. So filter, combo, and then it's like validate row. And then I'd pass it like the first row would be 0 to 8. And then you do the same thing for the second row, but it'd be 8 to 16. And then you pass in the validate columns. Whoops, I'm leaving out combo there. I mean, I'm pseudocoding it really fast too, so. So now we have like all 3 of our validations, right? And then it'd be like dot next to get the first solution. And we can unwrap it if we want. So that would get me like the first solution. This is the heavy like pseudocode version. So it's not 100% valid, and I don't even have a my vec. So like if I save this, it's going to start yelling at me. This is pretty readable. You know, you have to understand what's going on with the closure syntax and stuff here, but it's pretty readable. It's not, it's almost very English-like in some ways. The other way to do it, like another way to do it, not the other way, another way to do it is like for combo in my vec.iter.combinations 16. And then you can run through the loop now and you can say if validate, or you probably say if not validate row dot dot dot. I'm not going to type it all out again. If it's not validated, then you continue to the next one, right? If it's not validated the second row, continue on again. If it's not validated the columns, then we continue on again. And then finally we have a solution. So this is like an example of it's like a branch and bound algorithm, you can call it. And it's used to solve combinatorial problems like this. And the idea is that, you know, we're saying, hey, we already know this isn't a solution, so let's kind of keep going. Let's test the next one, right? There's probably a better way to do this for loop version, maybe, I don't know. But this was exceptionally slow. This was like minutes. Like I went and like brushed my teeth and came back and it was still looking for the first solution, When I run this version here with the iterators and the filters and everything, it's less than a second. And this iterator here, like if we remove the .next and we go to this with just the last filter, this represents an iterator of every possible solution. The .next just says, give me the first one, right? Give me the first solution. This comes back in less than a second. It's super, super fast. It's probably doing some auto vectorization or some SIMD or something. I don't really know. I didn't look at the assembly or anything, but that's an example of why I say in a lot of cases, when you're building out like this kind of like, well, we're going to build out one loop here, build out another loop here and track the index and everything. I feel like LLVM is smart enough that it's probably going to be able to better optimize the iterator version here. And in a lot of cases, that's probably going to be faster. Not in every case, probably. There's probably something where you can force it into, you know, if you really like dig down and look at the assembly it's generating, you can probably get something. But for the most part, everything I've ever seen in Rust, you should pretty much trust iterators. And they, of course, iterators have a lot of advantages by virtue of you not having to worry about indexing, right? So that just saves a lot of trouble without having to worry about indexing and all that. So you do get some advantages. So let me hop back over now. I'm glad you thought it was a good comparison, though. I tried to do the shorter version this time. I went on like a 10+ minute detour earlier, and I was like, I don't want to do the whole thing again. But it is an example of like, the logic is the same between both of those, between the for loop and the iterator version, but it was like orders of magnitude. And it really impressed me just how crazy the difference was. I was like, this logic should be the same, but when I'm running iterators with filters and stuff, it's just like, it's magic. It's crazy. All right, so let's wrap up here with the starting position and stuff, and then I'll actually back up to the stuff we were talking about earlier and talk just a little bit more about Rust as a whole before I wrap up the whole session here. So we have start position and exit. So we don't really want completely random starting positions, nor an exit that's deliberately far away on the map. So we're going to edit our town builder constructor to remove the additional meta builders that provide it. And then we're going to modify the build function to provide them instead. So let's take a look at that. Where are we at? Town builder, wherever you're at. We have level builders, so the naming has been a little inconsistent here. Let me rename this to town builder. And we have our chain here. We start with town builder new, and we're just going to get rid of the starting position in areas, just like that. Then we're going to modify the build, which is in here. So we're going to, this build rooms. And I guess we're going to do it before we do the screenshot thing. So we're going to say, we're going to get an XY index of the build data.width -5 and the wall gap Y. So we're just going to go to the right-hand side of the screen, the east, and it's going to be like right in the middle of the road. The main road. Okay. I got lazy and it didn't work out. It's like, will you autocomplete? Nope. So placing the entrance is going to be more difficult. We want the player to start their journey in the pub. But we haven't decided which building is the pub. So we're going to make it the largest building on the map. After all, it's the most important one for our game. So the following code is going to sort the buildings by size in a building size vector, with the first tuple element being the building's index and the second being its square tileage. So let's go ahead and take care of that. So let mute building size is a vec new. I don't feel like typing out the type. For I building, in buildings dot iter dot enumerate. Right, so we're going to push in all the building sizes there along with their index. Actually, it is still going to be... oh, whoops, no. That's my mistake. I started typing one thing and then I changed it. I changed my mind. Building size dot sort by. It's going to be a b dot 1 dot compare a dot 1. We're just multiplying the width and the height of the building. Yeah, we're just multiplying the width and the height of the building and getting the area, right? And then just sorting by the size. Very easy. So we are doing B and then A, so that gets us largest to smallest. And the text says the same. Note that we sorted in descending order by doing B and then A rather than... So by the way, I say this myself and then I look over at the text. Sometimes I do that repeating, but I figured this stuff out on my own and then I look over at the text and get like... It's like two different perspectives, right? So the largest building is building 0. So now we can set the player's starting location. We're probably going to pick the center of that. We're going to start in the pub. All right, so we're indexing back into the buildings with the index that we got from the sorted building size. We'll get the starting position equals sum position. It's going to be... Let me go down another line so it's more easy to read. So we're just getting the center of the building, basically. Yeah, that's it. Whoops. I'll be making them typos. We're just calculating the center of the building based on the starting X and Y values here, which is the pub 0 and 1. And the pub 2 and 3 are the width and height, so we're dividing that by 2. So we're calculating the center of the building. And that is the starting position now. And it's already being assigned to our build data starting position. So everything else already knows about it. We don't have to do anything with it. It's just going to work. It's magic. So let's go ahead and run that. And that's going to be our wrap up. That's going to be it. This is the start of the town. Doesn't have any people or anything yet. That's going to be for next time, I believe. But it's a good little starting town. Got little roads and everything. And there we are. We're in the building now. And I really like this. It reminds me of Fallout 3. I guess other Fallout games have done it too, but that's the first one I played, like a lot of people. When you walk out of the vault and you just see like the world open up before you, I like that. Good stuff. Alrighty. So let's just click back over and read the little wrap up here, and let's take a look at their little demo of the starting as well. Cool. So this chapter walks through how to use what we know about MapGen to make a targeted procedural generation project, a fishing town. There's a river to the west, a road, town walls, buildings, and paths. Doesn't look bad at all for a starting point. Completely devoid of NPCs, props, and anything to do, so we'll rectify that in the next chapter. Yeah, populating the town. So that'll be next time. I do these coding streams on Monday and Wednesday. It's going to be a few days, but I'm really excited about that. It's going to be good. So what I usually do here is I just skim through and take a look at like a little teaser. We have a barkeep showing up here. I know it's kind of tiny, but you can zoom in. Oh, the images don't resize much. Zoom in a little bit though. You see dudes in there. Scroll way down. Yeah, I can see a little happy face and stuff in the city there, or in the building there. It's gonna be fun. Yeah, we're like displacing people, like pushing them around. I love it. I'm glad you found it informative. I was also, since we talked about this a minute ago. Oh, cool. We have an abandoned house coming up full of hostile rats. That's going to be fun. That's going to be a good place to level up once we add experience in a few sessions. That'll be a good early game. Like, hey, go fight the rats. Cool. So this is going to be next time. It's a bit of a beefy section as well. So it's just going to be this one section next time, but it should be a lot of fun. So I will hold off a little bit on my normal full outro. Because earlier we're just talking a little bit about Rust, and Z-Sauce was saying. So originally, when you asked why did I do the test 2 string, I didn't realize at that point that you hadn't worked with Rust. So definitely, that makes a difference because there are the 2 string types. There's the string slice and the big S string. And maybe it made a little more sense when I kind of went back and looked at it. But there are the 2 string types. There's actually kind of a few more, but they're special ones. Like you have like OS related string types and stuff that are specific to the OS. So we don't really talk about that too much. But that's why I was doing 2 different kinds there, because I was showing how the same function can take both of them. Just a convenience thing, really. Just it was like a little side detour thing. And then, yeah, you said you hadn't coded in Rust, but you want to learn it eventually. And then I mentioned that I really enjoy it, and that I think there's a lot of virtues with the language that you probably don't hear as much, because performance and safety is what always comes up. That's big. That's what originally drew me to it. My background first was in AI and then cybersecurity. So me being interested in cybersecurity and being like, yo, there's this really performant new language that showed up that is also promising safety. You know, it's giving all these safety guarantees that other languages that are as performant are not guaranteeing. So I like that. You know, that's appealing to me. So that's what kind of brought me to it initially. But what I found is that for me, it's the best developer experience I've had with any language. It is still relatively new, so there may not be something that you want right away, or if you're wanting to do something like UI, it's still not the best in Rust, although it's getting better over the past couple of years. There are some really good frameworks, but you know, some of them are still not as mature as you'd like them to be. So there may be some issues like that. In those cases, though, if you really want, you can use bindings to other UI libraries and stuff. Like you could bind to Qt or whatever the Linux one is, I forget. GTK or something, is it? I think it's GTK. You could like bind to that stuff if you want. There are Rust crates out there that are perfectly valid for that. You know, so what I like about it is, to me, it is like the perfect blend of low-level and high-level features. One person I talked to in an interview one time, they described it as functional C, and I really like that description. You do get a lot of the great low-level stuff. You get a lot of the benefits of that kind of... You'll get people being very pedantic. It's like, it's not really functional because of, you know, pure functions and this and that. I don't want to get into the pedantic side of it, but in general, the functional elements of Rust are really good once you start getting your hand on them. When I started Rust, I was coming from like C, C++, and Java, because I had done some Java at my job. And it took me a while to really get my hands on, or like get my brain wrapped around some of the more functional stuff in Rust. But over the years that I've been doing it and I've gotten more comfortable with it, it's actually, I don't want anything else at this point. Like, it's a great blend of kind of the 2 different styles. And it gives you kind of as much power as you need. And what I did earlier with the filters and stuff is kind of a good example of that. where I was showing how the two different versions of that algorithm, one of them performed so much better than the other. And it was like honestly kind of easier to write for me because I'm so used to doing the filters on the iterators, filter them and do all this fun stuff like that. So there's a lot of cases in the tutorial here where I actually make changes based on how it's being written. I'm like, I don't like that. So do I have one here? Okay. No, I don't have one here. So I probably have a .any somewhere. No? Did I? Hold on. If, no. I have a .all? Where are we at? I know there was some of this hiding around somewhere. Damn, it'd be good to show the example, but I where would be a good place to look? Yeah, and what you said kind of sums it up. The language was architected in a way that provides a really good interface between the system and programmer. The community is good as well in terms of there's so many crates out there. Again, there may be some things like UI, which is not as mature as you would like right now, but it's getting there and it's going to keep getting better. And there's so many large companies that have already bought in. Microsoft is using it, Google is using it, Amazon is using it. All these like huge, gigantic corporations are using it. That's just going to help things out as it goes on, right? As these companies are adopting it and using it more and more. I mean, Microsoft has been embracing it quite a bit. They made the Rust Windows crate. It is an official Microsoft, sponsored is the word, but it is provided by Microsoft, and it is a Rust crate to the Windows API. Now, previously, there was someone who auto-generated bindings to the Windows API, and in a lot of ways, that's what the Microsoft one is too, but this is official Microsoft now saying, hey, you want to do Windows programming in Rust? We have the crate for you now. So it's really cool, like seeing that support really coming on. So the community is good there, but just in terms of actually writing the code, it's like three different things to me. It's like you got a lot of that low level access and stuff, but a lot of the way you're using some data structures and all that, you get the functional feel. In some ways, it's almost a little Pythonic at times, but definitely, more low level. I don't really like Python, but the syntax at times can feel a little bit like that in a good way. So, I mean, this is kind of the safety performance, yeah, but to me, it's even more like it's the ergonomics that go along with that. It's that I have such a powerful language that also feels good to write. That's the key for me, is that it feels good when I'm writing it. It doesn't feel like a chore. But a lot of people originally, they do feel like it has a high learning curve. Some people don't, but some people do think it has a high learning curve. And so at first, maybe it does feel like a chore, but once you get the hang of it, it's definitely, to me, more pleasant to write than like C++. I actually prefer C over C++ if I'm gonna pick between the two. But very specifically, I kind of like what I've heard called C-style C++. And that's something that game developers were doing around the early 2000s, where it's basically like, yeah, we'll use some of the STL stuff in C++, but we're still writing C-like code, basically. We're not going to do all the object-oriented stuff. And that's a big thing that I would say with Rust, is that it does not really support proper OOP. And I like that because I think OOP has its place. It can be okay sometimes, but it's very overused in my opinion. We have Java to blame for that. Java comes out in the 90s with however many millions of dollars or whatever they put into the ad campaign. They take over the enterprise world, and every business says, we have to do Java, so we have to do OOP, right? And now it's just shoehorned into every project that it doesn't necessarily belong in. And that was a big complaint. I'm being a little pedantic, but with Java and even C#, I do prefer C# over Java, but With languages like that, why do I have to make a class to print hello world? You know, that's a bit much. So I like that this is a language that wasn't afraid to say, we're not going to really support full OOP. You have some similar stuff with traits that are kind of like Java interfaces and stuff, but we're not really supporting OOP here. Like, that's not what you're going to get. And most people say that's a good thing, because today everyone's like, composition over inheritance, right? That's the modern phrase now. Like, let's get away. Even the creator of Java has said that, right? The creator of Java has said that that's one of the biggest regrets or whatever, that if he could redo it, he wouldn't have the full inheritance. He would just do like the interfaces and stuff. Like, if the creator of Java is saying that, then, you know, maybe they're onto something by not doing it here in Rust, you know, in other modern languages. Yeah, and little things like what, having to make a class to print hello world. I just, that's being pedantic, because you could really just make a main class and just write thousands of lines if you wanted, and it's not really like OOP. But the fact that I have to do the keyword like class and everything just to print hello world is enough that I'm like, why? I'm just printing something. Calm down, Java. So yeah, like Rust was not afraid to like take, I don't know if risk is the word, but it wasn't afraid to say, yeah, we don't need to do that. We have a design here. We have something we're going for. They took a lot of inspiration from functional languages, right? I mean, the original Rust compiler was written in OCaml. You want to talk about functional languages. So they weren't afraid to like show their pedigree and where they came from. And I think that's actually a strong suit. It's something that simultaneously feels different enough to be fresh and to be pleasant to write, but also similar enough to something like C++ that it's not the hardest thing to say, I'm going to learn this, you know. There's still enough similarities. But just like any other language, there's always going to be those gotcha things where it's like, oh, I thought this would work here, but it doesn't because X, Y, and Z, you know. Yeah, I wish I could, off the top of my head, think of a good example of... Actually, I can go to the room stuff. Room draw, maybe. Room corridor spawner. No, not corridor spawner. Room-based spawner? No. Give me a moment. I'll figure it out. Build rooms. Okay, this is an example. Oh, because I wasn't... I'm stupid. I know why now. Let mute okay. Yeah. This is actually the file I was already in anyway. So this is an example of one of the things that... There's nothing wrong with writing C-like code in C, but this is not C. And this is one of those examples where oftentimes I end up rewriting this in what I consider a cleaner style. I consider it to be more Rust-like, and I use the iterators and stuff. So this is one of those examples here where it's very simple. We have a variable we're calling OK, and we're defaulting it to true. And then we go through all the rooms and do some checks. And by the way, if I were writing it this way, I would also say break, because once we find an intersection and set it to false, we shouldn't keep looping through. However, good enough is good enough, because there's never going to be more than like 15 or 20 rooms or whatever. So like, what's looping through an extra 5 rooms or something? Like, it's not going to affect performance. Like, realistically, the human is never going to notice that impact, right? But that also still bothers me when I look at it, because I'm like, why would you keep looping? You've already made your decision. So yeah, we're setting okay, we're defaulting it to true. If we do find an intersection between rooms, we set it to false. And then if okay is still true after we do that, then we push the new room in. So we could rewrite that with iterators, and we could say like this. So all this code, we could say rooms.iter dot, and then all we care about is if any room intersects. So we'll say dot any, and then we're gonna call this other room. And then we're gonna say new room dot intersect other room. So what we've done here, we've got our iterator, and we're just saying if any room intersects, then we can't do this, right? So I can not that. If not any room intersects, then rooms dot push new room. And there we have it. Same code. To me, this is very C-like, right? We have to set a flag and this OK variable, and we assume it's true at first, you know, and then we go through, we loop through, we find if we need to change it to false, and then we check the variable, and if it is OK, then we do the thing. That's very C-like, and again, that's fine if you're writing C code. This is not C code, so we can swap it with something like this. So if any room intersects, and then I not it, so we're basically saying that no room can intersect, then we push the room in. To me, that's a lot more readable. I like that kind of coding more, and in some ways it's going to be better. I mean, you know, we're going to get the early return here. I do think it's more clean, yeah. Now you have to get the understanding of the way the iterators work, like any and all. Like you have to really know these functions here, because there's so many functions on iterators, and you know, so many of them are very powerful. Any and all are fairly easy. Just you have to say everything or one thing has to meet a condition. But I mean, we could do the filters. You know, we could chain. I don't use very much, but we can. I think like build. Yeah, we could build out a like chain up 2 iterators. Collect is common. What you'll see in that case is you'll see .iter, and then you might filter it. And then once you're done doing multiple filters or maps or whatever, you do .collect to pull it back into a new vec. So we have an example here where we have this vector or this array of A is 1, 2, and 3. We get the iterator, we map by doubling them all, and then we collect them into a vector of I32s. So it's a very clean way to just like do something to all the data and then pull it into a collection. And in this case, it's a vec I32, but you could really collect it to like anything. Here's a vec deck. You could collect them into, here's characters being collected into a string. You can collect them in all kinds of things. What else do we have over here? Just some of the main ones, like filter map is just kind of a combo of filter and map. Flatten is really useful sometimes. You see here we have like a vec with a vec inside of it, like this, actually with 2 vecs inside of it. So flatten's one way to get rid of that. You can also use flatten if you have like a vector of optionals or results or something. Let's see. Map is super common. We just saw a good example of that. Reduce. I don't use reduce too much, but it can be useful. Actually, fold and scan are pretty good. Because fold lets you, it takes 2 arguments, an initial value and a closure with 2 arguments, an accumulator and an element. So it allows you to, we have 1, 2, and 3 here, and they're using fold to do a sum. So they started at 0. Here's their accumulator ACC. And then for each thing we iterate over, we do ACC plus X, which is the current value. So we get 6 there. Now, I think there's also a sum. There is also a sum, but that's just a simple example of fold. Scan lets you do some similar stuff. It's a little bit different though. Takes 2 arguments, an initial value which seeds the internal state, and a closure with 2 arguments. First being a mutable reference to the internal state, the second an iterator element. And you can kind of do like whatever you want in there. You can do like powerful stuff here, step by and skip. So you can really like define how you want to move through the iterator. It's very, very powerful. Like, it's good stuff. That's kind of what I mean by, as you get used to all the different stuff that's available here, it's very nice. Like, and again, to me, if you're in C, like I said, you gotta do something a little more basic because you don't have some of this, right? Unless you build your own things from the ground up, you don't have some of these options. So I get that, but there've been a lot of those moments in the tutorial where I'm like, no, we're gonna do this more Rust-like. We have the options here, we're gonna do it. You need to implement a kernel for doing scan quickly on a GPU. Definitely doing some SIMD stuff if you use their iterators. Yeah, like that's the crazy thing, right? Like it's like magic because the tools are here for you as the programmer, right? Like, hey, we give you these iterators. If you use them, you're going to reap the benefits. So you might as well use them, right? Let's see. I probably have some other examples somewhere of some code like this, because I definitely made some changes. There's some interesting stuff back on the Rust side of things. Let me think about where it was at real quick. Which language was that you were doing? That you were saying because they made the iterators easy. In which language? Let me think about this real quick. We did something recently. Room Corridors BSP should do it. Yeah. Oh, CUDA. I did a little bit of work with CUDA, not too much. Back in a parallel processing course I took, I did a block matching algorithm. I can't remember exactly what you call it or the proper name, but it was a block matching algorithm to do video compression. And basically you divide an image up into like blocks. You define a block size, like, you know, say it's 20 by 20 pixels or something, right? Whatever. You define a block size, and then you can compare two images. So in video, you might compare two frames side by side, and then you compare the block with some amount of neighbor blocks as well, because motion might be happening. So imagine like you have a block and then you have all 8 surrounding blocks, right? You might compare to all 8 of those and say, oh, I see the same image has moved into the adjacent block, or an image that's like 93% the same. So you can actually store some compression data basically between those two blocks, and you actually save a lot of memory there, or a lot of storage there, by saying, okay, instead of saving 2 completely distinct frames, I'll just save how much this one changed from one to the other. So I did that in a few different ways, because the point of the project was to compare and contrast different approaches. So it was like some basic ones, like there are different for loops going on here. Which ones can I parallelize, and which ones are going to get the most benefit? And then one of the things I tried was CUDA. What was the other? What was the thing called? Like MPI or something? I don't remember. There's like a really nice framework though that it was kind of magic C. Like it was the most magic thing I've seen in C in a while, where like you just pull the library in, and then it's literally like a pound like parallel 4 in front of the loop, and it does it for you. Like that was one of the most magical things I've ever seen in C. It was like, oh, you're gonna just like automatically parallelize this. I think, yeah, Pragma, it's been quite a few years, but that sounds right. Yeah. Did you work with that? Did you work with something like that? It was good stuff. Okay, so one other thing that I will mention, since we're off on tangents and stuff anyway, is results and options. I feel like it's like MPI or something. What is MPI? Using MPI, yeah. So MPI might be it. Yeah, MPI and OpenMP. That's both of the things that I did. Both of the like simple C things that I did. And then I also did CUDA, and I think that was it. So MPI, doing a NID, a finalize, whatever. So I think OpenMP might have been the Pragma one you're talking about. Where's OpenMP? Because I remember that, yeah. It had been a while. What was that, like 2016? It's been a minute. It was like I totally, the moment you said that, I was like, whoa. It is crazy what like good C can do. Like that's why I like it more than like mediocre C++, you know. C is very simple. But like when you see someone do some magic in C, it's like, whoa. OpenMP, here it is. Yeah, Pragma OMP parallel. There we are. Let's see an example of like a loop or something. Pragma OMP parallel. Code here will be executed by all threads. Yeah, it's like, dude, what? You just did it. It's just magic. That's about how it is in Rust, though. Like, that's how you feel when you start doing things in Rust, and it's like, oh, it just works. That's part of what's so cool about it. It's like you get all this higher level stuff at the same time, though. I don't have Rayon is the big parallel library in Rust that everyone uses, and it's basically the same thing. So, you know, like we've been doing, I have this corridors vec right here, so I'd say corridors.iter, and I could do for each, right? Well, if I have Rayon imported, I could do like pair for each, I think it's called. That's the only difference. Like literally, that switches it to a parallel loop. And it's like, oh, that's okay, cool, thanks, appreciate it. All right, so I'll do the one last thing here, just because we're talking about some of this various stuff, and it's definitely like a critical thing. Obviously, borrow checker and all that's very critical, but this is one where I think I think a lot of people are initially kind of scared by it, but they feel like it's very syntactically heavy. But as you get used to it and you start learning some of the different ways you can deal with them, it actually is pretty nice. So here's an example here. So we have the result and option type, and that kind of prevents you from dealing with nulls and everything. Like you could still have some issues. In this case, we're doing a panic, so the program will crash, but we could do something else. We don't have to panic, right? We could do anything we want in here. But what I like about this is it's kind of this weird syntax. It's very odd at first, but it's very powerful because it allows you to do destructuring of a type and just like rip that type out in a safe way while handling the error, while handling the bad case. So what we have here is we have rooms, which is coming in from builddata.rooms. So what's going on is build data is this structure here, builder map. And not every kind of map has rooms because we have a bunch of different map generation algorithms, right? So some maps don't have rooms. They just like carve out sections of the map and it's really organic, like caves or whatever. So rooms is an option type, right? And I know option is in like modern C++, is in Java and everything. But the nice thing is you're not allowed to just not handle the case where it's none. You know, it's either some or none, and you have to handle both cases. And the same, whoops, drop something there. The same is true with the result, right? A result is either okay or error, and you're not allowed to not handle both cases. So there's a couple ways to do it. There is a syntax called if let, and there is a newer one called let else. And if let brings you down into like a layer of nesting. So we would say if let sum rooms, and then you'd say equal build data dot rooms, And then what that does is that takes build_data.rooms, the option, but it destructures it. And it says, oh, if it's the sum variant, get the thing from it and name it rooms. We could name this Yojimbo if we wanted, right? We could name it anything we want, because that's actually us destructuring it and getting the actual data out of the optional type. So then here inside of this scope now, I have Yojimbo, which is my vec rect, as you see here. And so I can actually do stuff with it. And then in the case where it's a none, where we didn't have any rooms, we could say else and then didn't have rooms, so panic or whatever we want to do, right? So it's like a really interesting, unique way to handle these cases where you're dealing with like the results and the optionals. And I think it feels very ergonomic, but it takes some time to get used to the... If let is kind of weird, but what really starts to make it click is when you understand pattern matching in Rust, because it's so stupidly powerful. And you can do it in all kinds of goofy places. It's one of the benefits of like everything being an expression, right? So for another quick example, or actually we'll contrast what I just showed with this here. The let else is a way where instead of going down into a layer of nesting, we're actually extracting the thing from here, from build_data.rooms. We're extracting it and we're naming it something. So again, I could name this Yojimbo. Doesn't matter, right? We're ripping this thing out of the option type, and now we have access to it in the outer scope. And this is nice because if you have multiple things you're dealing with, you're not going to keep going deeper and deeper into more layers of nesting, right? So it's a cleaner way to deal with that. As long as you know what you want to do and you have a good way to handle the none case. You know, in this case, we just panic, but you probably wouldn't want to do that in production unless it was like really, really busted, you know? So I mentioned like this is kind of strange, but what it actually is, it's part of the pattern matching system. And you could do all kinds of stuff on like this let else and everything here. It doesn't have to only be on options and results, but the example I'll do is still going to be with the options. So we could do a match statement, and we could do it on build_data.rooms, and it is an option. So the match is already yelling at me and saying, yo, none and some both need to be covered, and they're not. So I can have it autofill the match arms, and now we have both cases here. We have both variants, and you can put your code in here. So print line, and then we're going to call it, that's a weird, we'll get rid of that. It's a weird syntax to mean print the debug version of it. I'm going to call it potato because I can. And then down here, we would say like, we got none. So, oh, rect doesn't implement it though. Yeah, rect doesn't implement print, or doesn't implement debug, so we can't actually print it. But in most cases it would, just not in this case. I didn't know the data type wouldn't print it. We could do corridors, but it's not an option or anything. So this is like basic pattern matching, right? But it gets really powerful because if we have like a struct test, and it has x I32, y I32, z I32, and then let my test equal test, and then we'll have 1, 2, 3. Well, if I can type. So we have a test here with x, y, and z, 1, 2, and 3. We can do that pattern matching and destructuring on it, and it's actually really powerful. So, you know, you think of like C and C++. This is like the switch statement on steroids, right? So we can match on my test, and now we have to actually have some different patterns in here that we want to match against. So we know my test is a it is a test struct. So I'm going to say test, and then we're going to say X, 1, and we're going to say Y and Z. And then we'll print line X is 1. Now, this is going to fail, as we see here. It's non-exhaustive patterns because X goes from I32 min all the way up to I32 0 inclusive. You see the equal there. None of that's covered. We're only covering X as 1. So X also needs to cover all the way from 2 to I32 max. It is forcing me to cover all possible cases, which is good. So we could add another one here and say test X, Y, and Z. X is whatever. And now everything is happy, right? But we could do more. So what I did here, though, is I specified we want a specific value, and then Y and Z is whatever. So the cool thing is Y is blah, Z is blah, and then I can put Y and Z into the string here because we don't actually know what they are. We said if X is 1, get us Y and Z. Now, I'm going to rename these to prove the point a little bit. We're going to call that, no, not that. Oh, actually, no, that's what I wanted. Yeah, my bad. There we go. So now we're getting any Y, and I'm naming it potato. That's now like a variable internal to this scope here, and so I can print potato, right? But it is the I32. Whatever we set Y to here, that's the value that we're destructuring it. That's what it's called. So it's pattern matching and destructuring, and we can do that in all kinds of weird and interesting places. So I can also do something like, I can like destructure that struct, or you could do it with enums as well, because enums are really powerful here. You could like destructure those into other variables. You could destructure tuples. It's really powerful what you can do. And we could do more matches here. Like instead of just that, I could do, okay, well, I don't care about what X is, but I do want Y to equal 12. And I want Z to be whatever, you know. So now we have yet another one here. So yeah, it does do all the filtering and stuff. It like the way it complains about everything. It's like, yo, you're not matching everything. So we could do like all kinds of crazy stuff here. And if you match on a value, I'm going to be really lazy and we're going to match on my test.x because that's an I32. I32, it's a non-exhaustive pattern, right? So let's say we're going to match on 1 and do something. We're going to match on 3, do something, and we're going to match on 12. So if I do that, that's not exhaustive, right? So if we look at it again, it's actually telling me I32 min all the way up to 0. 2 is not covered because we left the gap between 1 and 3. 4 to 11 is not covered. And it says one more pattern. It's not showing all the patterns here, but I think you know it's going to be from 13 to I32 max. So like it really wants to make sure you don't leave these things out, right? But back to like the destructuring thing. Enums are the same, by the way. If you have an enum, and enums are dummy powerful in Rust. They're like C enums on steroids as well. But yeah, if we have something like this, we can do all these weird matches and like destructures and stuff in our match statement. We can match against strings. We could do all kinds of crazy stuff in here. And it's as you start learning that, as you start getting used to that, it's like how have I not used, like, how have I lived without this, right? I know, like, modern Java does something a bit like this, but it's not as good. That's generally the way a lot of these things are in Rust, is like, it's usually like other things on steroids. So the last example I'll give here is, let's get rid of the struct, and we're going to make this an enum test, and get rid of that here. And emergency broadcast system failure I32 testing I32 string F64 and then point X I32 Y I32. That's an enum for you. An enum here in Rust can have data all through it. Testing now needs 3 values: 12 testing.to string and an F64. And then matching on my test, which is now an enum, it's going to force me, I ignore all the yellow. It's mad because these to-dos are making it an unreachable statement. Like, it knows a to-do, if you reach a to-do, you panic because there's like, hey, there's no code here yet. So you'll panic. And that's why it's complaining. That's why everything's yellow. But, and it's also complaining that I'm not actually using any of these variants because I'm only using one of them here. But you see how we're able to pack in data into our enum. And we could do unnamed data here. It's like a tuple. And we can have named data here, which is why I called it point and gave it an X and a Y, because it's kind of like a point. And then all that pattern matching and stuff I was talking about can come into play here, where we have, like, if we're matching on the point variant, we have an X and a Y that's coming in, and we can either explicitly say, I want X to equal 1, 2, 3, or you could just let X and Y be variables that you pull into the scope. You could do however you want, you know. And we have, like, failure is just an enum that has a single I32. It's really interesting. And then we have our other enum types, like emergency, broadcast, and system, which are just regular old enums like you're used to in like C, with no real data associated with them. Now, why, like, the data there, you know, you might wonder why would you want that on an enum? Well, there are different reasons. I think more appropriately, these enums are something that would be called an algebraic data type, which is why it's always like, yeah, they're like other enums on steroids, right? So it's something called an algebraic data type, and it can actually be very useful. For example, what if you have things that do need data, but you only have a couple different variants of it, like std net IP address, and then we have a v4 and a v6. So let test equal v4. Actually, let me go back in here. I think there was a better function I could use for it. Well, I guess we could do this. But I don't know what the... I thought it took in... let me look at it here. Oh, it takes in octets. Okay. This is not the function I was expecting, though. Let me try something else. Oh, this is the one I wanted. I think this is the one I wanted. But is this still a member of the... Is this still one of the enums? It goes down to this. So it may not be one of the enums. I might have been wrong on that, but one of the examples you often see, if I am wrong, I am, that's fine. But one of the examples you often see in the documentation is enum IP adder, and you have IPv4, and it'll be U8, 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 and U8, and you'll have IPv6, and I can't remember what it's hex, right? I don't remember. I actually don't remember what the format is. I should know, but I don't. But whatever it is, you can have the two variants that have the data for the IP addresses packed into them. And so then you're simultaneously matching on it and getting the data. Is it like 6 things of hex or something? I don't know. It's goofy. I should know, but I don't use them that much. So that's an example of like where that can actually come into play, because it does make sense then. You might have one or the other. That's a good use for enums, but now we actually have the data associated with it at the same time. It's very, very convenient, very nice. Good stuff there. So if we look at the enum documentation thing that pops up, does IP address show up? I'm not seeing it. But yeah, we have complex enum. Nothing, something with the U32, lots of things with usual struct stuff and blah. I love it. Location could be unknown, anonymous, or known with a set of coordinates. I mean, that's like that's a decent use case. The first enum is the usual kind you'd find in a C-style language. The second shows off a hypothetical example of something. Yep. When data follows along with a variant, such as with Rust's built-in option type, which, by the way, we should look at. No, don't open website. So we have an option here. And can I not get to it? The option type, the built-in option type that's so powerful and drives a lot of Rust and stops us from having nulls, that just happens to be an enum. Yep, there it is. You said it was a sum and none thing. Yep, they're right here. It just happens to be an enum, and that is like the thing that gets rid of nulls in Rust, because it forces you, there's no matter what, you have to deal with the none type. So that's why there's no nulls unless you're going down to like the low level memory stuff where you do like std, mem, ptr, is it? Hold on. No, where's it at? Oh, it's std pointer, and then null. You can like make a raw null pointer, but you start getting into dangerous stuff. But if you're in like the Windows API or something, you don't really have a choice, right? That's how OSs work. That's why the language can still do it. But like the chances that you're doing that in like 99% of the time in Rust, like you're not doing that, you know. Alrighty, that was kind of fun, just clowning around with this for a bit, showing some of the different features. I mean, maybe you get the idea of what I mean, though, and like the ergonomics and stuff. I really like what you said. I'm gonna read it aloud just so it's there, because these go up on YouTube as well. It says, this is making me think of all the ways programming languages have constrained the way we think of stuff just because the language itself was not expressive enough. And that's a great, yeah, that is a very great way to kind of think about what I was trying to say with this language, is that it is expressive in a lot of ways that allows you to do the things you want to do without, you know, feeling like you're jumping through too many hoops usually. Again, a lot of people early on don't like the borrow checker and stuff, but you get to a point where you don't even think about it. I don't think about the borrow checker anymore. It's like, unless I'm doing something really goofy, I don't care about it because I'm so used to it now, right? I've been using it so long. And once you get to that point, you don't really feel constrained anymore because you're thinking around those memory constraints, you know. You're thinking about, like, just by default, you're like, oh, if I do this, it's going to be mad, so I'll just write in this way. And it doesn't feel like you're jumping through a hoop. It might sound like that the way I'm describing it, but what you're actually doing is you're writing better code, right? Because the reason it's mad at you is because that's like a memory vulnerability. You know, it's like a bad shared reference or something that you shouldn't be doing. That's why it's mad. So once you get used to that, you know, and you're not making those mistakes, it's like, oh yeah, this is way smoother. I like it. By the way, I didn't show it, but result is the same as option. It's just error. It's okay and error, but it's also like just an enum. And so if you have a function that can fail, then you make it return a result. And then the caller of that function can just check to see if it was an okay or an error, but they're forced to deal with both. That's the critical thing. You can just say, hey, I don't care if you crash, but you have to tell it to do that. It doesn't just like accidentally crash without you knowing. Like, you have to do something like a panic, or you have to unwrap it, which is the dangerous thing, right? Build data dot rooms, that's our option, and then unwrap. It returns that contains some value, consuming the self value. Because this function may panic, its use is generally discouraged. And then there's other options that we can do here, like unwrap. All these other ones, unwrap, well, I don't know about unchecked, but yeah, calling this on none is undefined. So let's forget about that one. Unchecked is usually kind of goofy stuff. You want to avoid it unless you have a really good reason. But unwrap or default, or unwrap or else, those are all like safe ways to do the unwrap where you won't panic. So those are like perfectly valid to use in production code. But unwrap, unless you know you want the program to crash, that's pretty discouraged. I don't like seeing that. It shows up in the tutorial. I'm like, no, don't do it. I'm cringing over here. Because I'm like, if I'm generating a map for the game, and let's say we try to unwrap something and it crashes, if I were like shipping this to the player, what I would rather do instead of crashing is have it default to some kind of map, because the player would never know. Have it just make a simple map that you know is going to work, force it into like a happy path at that point, rather than just shutting down the whole game and crashing it. That's kind of the approach I would want to take a lot of the time. But there are a lot of unwraps in the tutorial. And I always call it out every time. Like, maybe we could do this instead. Maybe we could do that instead. But it is a tutorial at the same time. So sometimes you want to take the shortcut and just, hey, let's get something working. All right. I'm glad you appreciated the additional tutorial and stuff. There's a lot of these. This is the 27th session of this tutorial. I did a couple other things as well, so they're all on YouTube if you're interested. Everything I do at this point, personal programming and on my streams and stuff, is all Rust. At work, my different jobs, I've done Java, C++. I've squeezed a little bit of Rust into a couple jobs, some Python, some Perl. Not happy about that one especially. Some other goofy languages. Mostly like C++ and Java would be the main ones. But when I'm writing at home or whatever, this is it, you know. Because I just enjoy writing it so much more. Yeah, if you're interested, it's all over on the YouTube channel. I know the link popped up in the chat a minute ago. So there's a lot of these. You can definitely get more context on how things have gone with this tutorial. These streams, well, I'll do this part of the outro. I'm gonna go wrap up for real. That way I can wind down before bed and relax a little bit, because I got my second office day tomorrow, so I got to get up at the ass crack of dawn and drive an hour to get there to beat traffic. So thank you, as I always say, thank you to anyone who showed up, whether you are lurking or chatting. I do appreciate it. It's been a good chat here, Z-Sauce. If you are watching this right now and you're new and you like Rust, you like these roguelike tutorials or anything like that, some of the games I'm playing, like Dwarf Fortress, Caves of Cud, I'm currently replaying the whole Metal Gear Solid series. I do Genshin Impact every Sunday night. I do play all sorts of different games, but those are my current games. So if any of that's interesting as well, definitely hit that follow button. Come hang out. It's a good time. You can also head on over to YouTube, where these streams go up 2 weeks after they're live here on Twitch. And if you're in the future watching on YouTube, congrats on being in the future. While you're over there, I'd appreciate if you do all the fun YouTube stuff. Like, subscribe, hit that notification bell, leave a comment, because I do read and respond to my comments. I really do appreciate them. And lastly, if you care that much, you can follow me on Twitter. I do tweet when I go live, and I do have some people occasionally complain that Twitch notifications are very unreliable for them. Like an hour or more after I go live, they'll get a notification. So that's another way to see when I go live. I don't do too much else on there, so it won't be too spammy. But I definitely I tweet almost every time I go live. So yeah, that is about it. I don't think I have anything else to say here. So next time we'll pick this back up with the populating the starting town. We're getting some NPCs and stuff. Get the pub set up. It looks like we'll have maybe some furniture or something. I don't quite know yet. We just skim it. I don't like to read too much ahead, but yeah, we have a keg, a table, a chair. It's going to be good stuff. Looking forward to it. We're going to have living bystanders coming up. We're moving closer to getting actual experience, so we'll be leveling up and stuff. That's going to be fun. Really cool. Still quite a few sessions on the way, but we are over the halfway point now. So this is starting to kind of not wind down. There's still a lot of work to do, but it's starting to get to that point where the end is becoming in sight, right? It's kind of there now. It's still going to be probably maybe a month and a half to 2 months to get through these, depending on how short some of these are. So we're going to have a lot ahead of us, but at the same time, it gives me room to start thinking about what I'm going to do next on these streams. I am using these streams as a way to keep me working on different game development concepts and everything. Practice. I'm learning at the same time, and I'm trying to understand it. So I'll sometimes slow down and break things down if I'm not understanding it all the way, and I try to give my take on it as well as the text here. And I'm doing that so that I can make my own game, right? So I can learn these concepts and really understand them and apply them for something that I'm going to make of my own. So I'm thinking about what I'm going to do for the next thing, but we still got a lot of time to figure that out. All right, enough of me rambling. I am going to go wind down for the night. So until next time, have a good day, have a good night, whatever it is, wherever you're at. Take it easy.
I hear it's amazing when the famous purple stuffed worm in Flapjaw Space with the tuning fork does a raw blink on Harry Carey Rock. I need scissors. 61.